Hi learners, welcome back to GATE coaching class from S.A. Engineering College. Myself, Dr.R.RADHIKA, Professor, Department of ECE, S.A. Engineering College. So in this session, we are going to discuss about sampling. Before that, the vision of our institute is to education and research management sustainable solutions, and mission of our institute is this, and department mission. So in this session, we are discuss about sampling theorem. So before we enter into sampling theorem, what is the need of sampling? Why we go for sampling? Why we need sampling? ADC. So what is an ADC? Analog digital conversions. So generally signals are in analog in nature. So for example, speech signal or weather signal. These signals, natural signals, are in analog nature. To process the analog signals by digital means, it is essential to convert them into discrete time signals and then to convert into sequence numbers. So analog signal is first converted to discrete time signals and then it is converted to digital signals. The process of converting analog signal to digital signal is called ADC, analog digital conversion. So what are the steps involved in this analog digital conversion? First step is sampling, second step is quantization, third one is coding. This is an analog signal which is converted to one digital signal or discrete time signals with the help of sampling. So what are the types of signals? I already told that there is an analog signal which are natural signals, and then analog signal is converted to one discrete time signal, and then there is one more signal called digital signals. So what is an analog signal? Analog signal is continuous in time and amplitude. Both time and amplitude parameters are in continuous nature. The example for this analog signal is voltage, current, temperature. And digital signals, discrete both in time and amplitude. So this is a time and amplitude, both parameters are in discrete format. Example for this is attendance of the class, digitized analog signals. So attendance of the class means resistor number 1 is present on 20th and resistor number 2 is present on 20th. Like that we can predict put the attendance in that. So attendance of this class is in digital format. Discrete time signal, discrete in time, continuous in amplitude. So time is in discrete format, amplitude is in continuous format. So hourly change of temperature is an example for discrete time signals. The analog signal is converted to digital. There are three steps: sampling, quantization, and then coding. So sampling, first we discuss about sampling. So what is a sampling? Sampling process is to continuous time signal is converted to discrete time signal by taking samples of continuous time signal at discrete time intervals. See here, the continuous signal is converted to discrete time signals with the help of equal sampling intervals. Discrete time intervals. So x of nts is equal to x of t. Capital T is an sampling interval and x of t is an analog input signal. Sampling is a process. So this process maintain and sampling theorem. So what is a continuous time signal? Can be represented in its samples. Continuous time signal can be represented in samples and can be recovered back when sampling frequency fs is greater than or equal to twice the highest frequency component of message signal. So one more thing we have to maintain here. This is band limited signal. The signals are considered as a band limited signal. So fs, sampling frequency, should be greater than or equal to 2fm. fm is a maximum frequency. So that is highest frequency component of message signal. So once again I repeat, continuous time signal can be represented in its samples and can be recovered back when sampling frequency fs is greater than or equal to twice the highest frequency component of message signal. So this is a sampling theorem. Wherever we go for this ADC conversion, the first step is in sampling process which maintains this sampling theorem. So how this analog is converted to sampling? By maintaining a sampling theorem. Consider a continuous time signal x of t. X of t is a continuous time signal because in this analog signal the time and amplitude both are in continuous format. The spectrum of x of t is band limited. I already told that. One important thing we have to maintain is the spectrum is in band limited format. 2 fm hertz, that is the spectrum x of t is 0 for omega fm is greater than omega m. maximum frequency means that is equal to 0. So that is called as a band limited signal. Sampling of input signal x of t can be obtained by multiplying x of t with an impulse train. By multiplying x of t with the impulse train we call it as del of t of a period ts. The output of multiplier, because the x of t is multiplied with del of t with a period ts, and the output of this multiplier is a discrete signal called sampled signal. So x of t is multiplied with del of t, we get the output as a discrete time signal which is called as sampled signal and is represented by y of t. See here. So this is x of t, continuous signal, analog signal. X of t is multiplied with del of t. This is a del of t with a period of ts. So x of t is multiplied with del of t, we get y of t. Y of t is a sampled signal. See here, based on the x of t, the signal is sampled like this. We get a sampled output y of t. This is in spectrum of that. So how this sampling process is done? There are three methods of sampling. One is called impulse sampling, another one flat top sampling, the third one natural sampling. So what is that impulse sampling? Impulse sampling can be performed by multiplying the input signal x of t with impulse train of del of t with a period ts. See here, this is a continuous signal x of t multiplied with impulse train, same amplitude with a period of ts. We get the output y of t, that is sampled output xs of t is like this. So this is called impulse sampling. So what is that flat top sampling? Flat top sampling means during transmission, noise is introduced at top of the transmission pulse, which can be easily removed if the pulse is in the form of flat top. Why we go for flat top sampling? Because during transmission, noise is introduced at the top of the transmission pulse, which can be easily removed if the pulse is in the form of flat top. So we go for flat top sampling. The top of the samples are flat, that is they have constant amplitude, hence it is called as flat top sampling or practical sampling. So x of t, it's in continuous format, and flat top sampling is multiplied with x of t, we get a sampled signal like this. So all the top of the signal is flat top, so we call it as flat top sampling. The last one is natural sampling. Natural sampling is similar to impulse sampling, except the impulse train is replaced by pulse train with a period of ts. So this is an impulse train with replaced by pulse train. So the remaining thing similar to an impulse sampling. So continuous signal x of t is multiplied with natural sample signals, and then we get the sampled output. See here, the flat top signal with the top is flapped, but in this case it's a form in the continuous signals, impulse sampling method. Now we enter into a sampled questions, previous year gate questions. Consider the signal x of t that is equal to cos 6 pi t plus sin 8 pi t, where t is in seconds. The Nyquist sampling rate in samples per second for the signal y of t equal to x of 2t plus 5 is, see here, cos 6 pi t sin 8 pi t. So cos 6 pi t sin 8 pi t means 8 is the maximum frequency. So 8 pi by 2 pi, that is 4 hertz. In this 4 hertz means 8 hertz in the sampling frequency, and the Nyquist sampling rate is 8 into 2b. So Nyquist sampling rate formula is 2b. So that is 2 into 8, 16. So the answer is 16. A continuous time function x of t is periodic with period t. Continuous time signal x of t is periodic with period t. The function is sampled uniformly with a sampling period ts, in which one of the following cases is the sampled signal periodic. So from this output, one signal is in periodic format, that is b equal to 1.2 t is the answer. T is equal to 1.2 t, that is an answer. This signal is a periodic nature. The third question is x of t is equal to cos 10 pi t plus cos 3 pi t be sampled at 20 hertz and reconstructed using an ideal low pass filter with a cutoff frequency of 20 hertz. The frequencies present in the reconstructed signal is, So the reconstructed signal followed the sampling theorem. So with the help of sampling theorem, among these frequencies, which one belongs to the problem? X of t is equal to cos 10 pi t plus cos 30 pi t. So 10 pi t, 30 pi t, 10 pi t, 30 pi t, 10 pi by 2 pi 5 hertz, 30 pi by 2 pi 15 hertz. So the answer is 5 hertz and 15 hertz only. Answer is 5 hertz and 15 hertz. Next problem is a band limited signal with a maximum frequency of 5 kilohertz is to be sampled. So maximum frequency FM is 5 kilohertz is to be sampled. According to the sampling theorem, the sampling frequency which is not valid. So what is the sampling theorem here? Fs should be greater than or equal to 2 FM. FM is 5 kilohertz. 2 FM is 10 kilohertz. 5 into 2, 10 kilohertz. So Fs should be greater than or equal to 10 kilohertz. Here the option is 5 kilohertz, 12 kilohertz, 15 kilohertz and 20 kilohertz. Greater than or equal to 10 kilohertz. Greater than or equal to 10 kilohertz means B is a correct option. 15 kilohertz C is also a correct option. 20 kilohertz D is also a correct option. So these three things are valid. Which is not valid means 5 kilohertz is not valid. 5 kilohertz is not valid. The next question is, a band limited signal is sampled at a Nyquist rate. The signal can be recovered by passing the samples through RC filter, envelope detector, PLL, ideal low pass filter with appropriate bandwidth. So usually we prefer a low pass filter before the sampling. So ideal low pass filter with appropriate bandwidth is a correct option. And then flat top sampling of low pass signals. Flat top sampling of low pass signals gives rise to aperture effects, implies oversampling, leads to aliasing, introduce relay distortion. So among that, gives rise to aperture effects is a correct option. Gives rise to aperture effects. Then the last question in this, a 1 kilohertz signal is flat topped, sampled at a rate of 1800 samples per second, and the samples are applied to an ideal rectangular low pass filter with cutoff frequency of 1100 hertz. Then the output of the filter contains only 800 hertz component, 800 hertz and 900 hertz component, 800 hertz and 1000 hertz component, 800 hertz, 900 hertz and 1000 hertz components. See, from the options we come to the solution. 800 hertz is the minimum one. So what is the maximum thing? So maximum thing we get it from the sample at the rate of 1800 samples per second. 1800 samples per second divided by 2, 900 hertz. So 900 hertz, 800 and 900 hertz components is the correct option. So we'll see the remaining things in the next session. Thank you.